There, now I'm going to start recording officially and hope that it gets captured. So, hi, Zoomers. There's no rumors today. It's Dr. Mommy in the house. So, Huey and I have been home all day, actually, because he only had school this morning, except he woke up with a stuffy nose. And given the weather, I decided he'd just stay home with me. So, it's a bonus home day, the class before spring break, due to snow, because that's how we roll here in Iowa. Anyone going to go skiing on spring break? No, yeah, I don't like skiing either, but you could. Like, at least not the hilly kind, like the cross country kind. That could happen. So let's see here. You should have gotten, besides the email this morning announcing that we are switching to a Zoom only format so that I can be Dr. Mommy. The other email you should have received is with respect to your projects. I have attempted to put together a schedule, and I believe so far we're in good shape. I will reconfirm once I hear back from everybody about their dates. And as I mentioned before, I will get you feedback on your outlines in the order in which you're presenting so that the people who are going first can get my feedback first. With respect to the presentations, I still plan to do it in a hybrid format and that you can attend class either way, but if you're presenting, I would prefer that you are physically there. That way everything is constant across students. I will not be putting your presentations on YouTube, so don't worry about that. If you want me to, I could, but I would not do that without your permission. My plan is to record the usual way where it's just the screen share and the audio and host the recordings inside Icon. That way the class has access to them, but then the outside folks don't have access to them. The reason that recording them will be important is, as I mentioned in my email, each of you is going to be responsible for doing a peer evaluation of someone else's presentation. So the recordings will allow you to go back to it, maybe take better notes, or if you have to miss that day for whatever reason, then you can still do the evaluation. Sound good? Good so far? Excellent. Let me double check the recorder. Now I'm paranoid. Can someone say hi again real quick, please?
Hello.
Excellent. Okay, watching the green lines move makes me feel much more secure about the recording actually happening. And I had the foresight to yesterday go to campus and grab the good laptop on when I was out running errands so that I could actually do this successfully. So hopefully I haven't jinxed myself. Anywho, what were we talking about on Tuesday? What do you remember? Let me scroll back up to the top here. As usual, I will take words, gestures, letters, anything that you can think of that we talked about last time. I'm watching the chat, or you can talk. Your call.
Yeah, I remember that we discussed that
Oh,
the
Vladimir, I can't
time.
hear you if you're talking.
Sorry, can you hear me now?
You all can hear him? Okay, I can't hear him.
I think so.
Yes,
Why
I
can't
can
I
hear
hear
you.
him? Hang on. It's my problem then.
Yeah,
I knew I
no,
jinxed
no worries.
myself. Why doesn't this speaker want to go? Okay, let me try this one. Can someone talk again?
Yep, can you hear me now?
I'm not hearing you. Christ. I heard you just a minute ago.
No. Okay,
My
but
goodness.
you can tell me. No worries.
Okay, one more time. Someone talk to me.
Now, can you hear me?
Goodness gracious. Talk to me one more time.
Hi, can you hear me?
Yes. Okay.
Yeah, okay. Yeah, no,
Excellent.
I just wanted to mention that last two classes we have been discussing that time varying predictors can have between and within person variance, and we can include fixed effects at both levels representing their respective effects.
Yes, exactly that. For the same reason that we have to care about longitudinal outcomes and their sources of variability between persons versus within persons, we have to care about that problem with longitudinal predictors between versus within. So there's basically two main ways of setting up the model. You can use observed variables or latent variables. If you're using observed variables, then you can do either person mean centering or grand mean centering. And today we'll start with person mean centering and see how far we get. That work for y'all? Okay, that's the gist of it, basically. So rather than review through the slides, I thought we'd jump into the example and do review and additions that way. Does that work? Sound good? All right, so as you may or may not remember, these are fake data that I simulated based on real data that were described in this publication. We're looking at a measure of physical well-being with respect to management of diabetes and type 2 diabetics. And so their glucose the next morning is the outcome variable of various time varying predictors that were collected the previous day for a 3-week period. And this outcome is an example of a fluctuating outcome, not a change outcome, meaning that some people are higher or lower in their glucose, but it's not an intervention. It's just an observational design. We're not trying to fix their diabetes or anything. They're already getting fixed for that with whatever medication and stuff that they're receiving. So in this story, time is basically irrelevant in the sense that nothing is going to be conditional on time zero. We're not worried about individual change because there isn't any. We're purely focusing on the extent to which daily negative mood can predict daily glucose and how those relationships would be expressed at the between person level versus the within person level, and then whether there are gender differences in the extent of those relationships. So that's the story. I believe we had the strength to get through the empty model last time. Does that sound about right? And we figured out by looking at glucose as an outcome as well as negative mood as an outcome that glucose had an interclass correlation of about 0.69, which means 69% between person, the rest is within. And the negative mood predictor also had an interclass correlation of 0.39, so more within than between, but some of both. So quick review, what interclass correlation would tell me that I don't have to worry about differentiating between and within effects for this time varying predictor? We got 0.5 as a guess, 1 as a guess, a 0.5 taken back. So an ICC of 1 would tell me that the predictor is all which level? This is a finger question. 2 or 1? Yeah.
Between, if ICC is 1,
yeah,
it's all between.
Yeah, if the ICC is 1, it's all between. So that's the only kind of relationship that it can have is between. If the ICC is 0, then it's all within, and the only kind of relationship that it can have is at level 1. So anything between 0 and 1 for predictor means we have to worry about differentiating its effects at each level, which is going to be most of the time. So here's one strategy with which to do so. So part 2 here, this is page 2 of the handout. I have my model that is now including a predictor at both levels simultaneously. And I do that because conceptually what I've done, I think of it as I'm going to add mood as a predictor. But to fully appreciate how mood would predict glucose, I need to have it at both levels. And the reason that I don't have to worry about the effects changing if I added it one versus the other is that these two predictors that I'm about to put in the model are uncorrelated. They are created to be orthogonal. So we are literally carving up negative mood into the between person level 2 part, the within person level 1 part, and putting both of those parts as new observed predictors in the model. So the notation then, I've got glucose, TI as usual, time with an individual intercept at level 1, and then an individual slope of negative mood, and note the notation here. So I am describing the idea of person mean centering by saying that time varying mood has subtracted from it the person mean of mood, so the I subscript with the bar over it. Some people put dots in their notation. It'd be like dot I. I don't like the dots. I find them confusing, so I just left them out. So mood with an I subscript and a bar over it means person mean mood. That was a variable that I had to compute as the average across rows for the same person and then add that to the data set. So every row for a person has a constant for person mean mood and a time varying mood for this part. So then the end result of this centering process is that we have subtracted out all person mean differences in mood, all level 2 essentially intercept variance in this predictor. And what's left is going to tell us about fluctuation in mood relative to one's own usual level. So when this predictor is at 0, you're at your mean. When this predictor is positive, then you're above your mean. And that seems a little weird to think about more than usual without putting usual into the model. So that's what is happening then at level 2, is that person mean mood variable is being used as a predictor. And I have the -0 here just as a reminder that if 0 is not a meaningful value, you should center it at a constant such that it is. So gamma O1 then is going to tell us the between person effect of negative mood, the idea of whether differences between people as a function of their average grumpiness is related to differences between people in their glucose. And how would I describe the slope of within person mood at this point, given this equation? I'll let the arrow point right to it. I'll turn it into a multiple choice. The slope is either fixed, random, or systematically varying. Fixed, indeed. Everybody gets the same. So this model is saying that everybody gets the same bump to their glucose that next morning as a function of their negative mood. So it's a fixed constant at this point. Same thing with the slope of mood at level 2. It's fixed as well, and pretty much that's its only choice. You could have fixed or systematically varying, but random level 2 slopes are very difficult to estimate, and they don't mean the same thing as a random level 1 slope. I would say they're impossible, but that's not quite technically true. So then to implement this stuff in the code, I've got stata code and R code as usual, just the R output though to cut down on some redundancy. So I've got both of my predictors here, within person negative mood and person mean negative mood centered at 0. The reason that I don't have a 0 after within person negative mood. So my usual convention when I center predictors is to take the centering constant and stick it on the end of the variable name. That way I know what my centering was. Does that sound familiar? Yes. Gesundheit. So I don't have a constant at the end of this variable name right here. I don't have a 0 there or a 3 there or whatever. Why is that, do you think?
Because you are using the mean of that variable?
I'm using a variable, not a constant, as the centering point. Yep. Question, why is the intercept mood -0 and not mood minus the average mood overall? Wouldn't for usual be the average in general? So this mood variable is actually scored in a z-score metric where the mean was already 0 and the standard deviation was 1. And so a mood score of 0 represents the average in the latent variable metric that we had calibrated this on. Otherwise, yeah, like if mood was, say, like in my book, chapter 8, I think I have like a Likert scale type of thing. I think I centered it at 2 or something because that was like the mean of the scale or close to the mean of the scale in that example. So just the -0 is just a reminder that you need to center the level 2 predictor the same way as you would center any level 2 predictor, because this is functionally a time invariant, excuse me. Okay, so within person negative mood without a constant at the end of it because it's not centered at a constant, it's centered at a variable. Only a random intercept. I have this in here not because I need it, but as a reminder to you, this idea of residuals, that is structuring your R matrix. So in these sorts of fluctuation studies, you might need some kind of residual covariance beyond just the intercept for occasions that are closer together. I didn't need it in this particular example based on the way that I generated the data, but this is just in here to remind you that this is something that you would have considered in the first place. But it will, stata when you run the output will say, I'm just going to ignore that because it isn't necessary. Let's see, we're using REML because we can. So I'm asking it to save the results from this model for a future likelihood ratio test. I am also lumping the two slopes together for a joint hypothesis test as to whether mood predicts glucose, because to answer that question requires two different slopes. I am relabeling two of the slopes on purpose so that I can generate an alternative model that has the same parameter estimates So these are just relabeling within person negative mood and between person negative mood that slopes are going to become. The new one here is the only one that I actually would need to ask for as a linear combination. So this is the contextual effect that we're sort of skipped over a little bit, but I want to plant the seed that you can get to a contextual effect even if you use person mean centering. Last but not least, I'm saving predicted outcomes to the data set so that I can correlate those predicted outcomes with the real one, square that correlation, and that turns out to be a total R square. So a more global measure of effect size for how effective mood is in predicting glucose beyond just the proportions of variance explained at each level. Okay.
Lisa,
yeah, go ahead.
sorry, but what's the meaning of that small in those lines?
Oh, the smalls?
Yes, what is that?
Okay, so thank you for the question. I hate Stata for doing this to you, by the way. These commands right here in the model instruct it to use denominator degrees of freedom. So it switches from providing z's and chi-squares into providing t's and f's. And in particular, it's using the Satterthwaite method to estimate denominator degrees of freedom, which matters much more for level 1 predictors than level 2. Now, you would think that because I asked for this to happen in the model, that any post-estimation commands would also use those options, but you would be wrong. So the small, comma small, is like, hey, can you go up here and make sure you're using whatever degrees of freedom method I had asked for in the model so that it stays internally consistent. Otherwise, none of these tests would be using T's and F's. They would all be using Z's and chi-squares. So, yeah. Other Stata questions? Okay. And in R, I've got the pieces here. So I'm using Elmer in this example because I can. So there's two main ways to estimate multi-level models in R. There's probably more than that, but the ones that are used most commonly is the Elmer function within the LME4 package. And it has an add-on to it called Elmer test that allows us to use to get Satterthwaite degrees of freedom for everything, and that works really well. The downside is that Elmer does not have an R matrix that you can customize. It only allows a diagonal R matrix. So if you had to have had residual covariances in the R matrix or something like that beyond a random intercept, we would have to switch to a different package, NLME, and the function within that is called LME. That package, I have had not good luck in getting it to actually do Satterthwaite degrees of freedom correctly. So it's like you can either have a custom R matrix or you can have the right degrees of freedom, but not both at the same time. All right, so I'm asking for -2 log likelihood and a summary. Here's my model, glucose, my fixed intercept, my 2 fixed slopes, and only a random intercept to start with here. All right, so let's look at the fixed effects then. So we still have a lot of variance in the intercept and a lot of variance in the residual. We'll look at the change in those relative to what they started in the empty model in just a second. But let's talk about what these things mean. So the intercept is the expected glucose. It is 4.93. For whom and when? In this kind of model, what does the reference point or group become? Who is this the intercept for, is the question. Given the centering and the creation of these variables. This isn't meant to be tricky. Can you still hear me? Yes, everyone's just looking down.
Yeah, to me, Lisa, but I cannot remember the predictor. What is the meaning of the predictor? Sorry.
Negative mood.
Okay, so to me, that intercept would be the glucose level for someone with a mean of mood at 0 or a z-score equals 0 on a regular day.
Yes.
Or,
so Yep.
Usual day. Okay.
Yes, regular day or usual day. More technically, when they're at their mean, but I like the idea of a usual day as a more colloquial way to describe it. So, yeah. So, this is the expected morning glucose for somebody who tends to be average relative to other people in their mean levels of mood. So, sort of an average grumpiness as a trait of a person. And then, when within person mood is 0, is when you are at your own mean. So this is on a day when you're at your mean for somebody who is of average negative mood relative to everyone else in the sample. So average person on an average day, so far not differentiating anything by gender. Okay, first one then, let's see, let's do level 2 first. Not win, thank you very much. Let's do this one. So the coefficient that goes with person mean negative mood, which has been centered at 0, is 0.07. It is significant. So how would I talk about that? It's just a slope of a predictor, so you know the answer to this.
I would say this is the increase in glucose level as negative mood increases for an individual.
For an individual. See, this is where it gets
Yes.
tricky, because as negative mood increases is no longer specific enough. So we have to work hard to keep the reader or the listener with us as we talk about sort of the levels of mood. So glucose on average across all the days, because this is a level 2 effect, it's bringing everyone's trajectory up or down by a constant amount. Glucose on average goes up by 0.07 for every unit grumpier someone is than other people. So every unit person mean mood higher. So this is differences between people on average in negative mood and how that translates into differences between people on average in glucose. So people who are grumpier than other people tend to have higher glucose. 0.07 per unit person mean mood. So this one then, it's a small number, but it's also significant. These are dealing in log glucose units, so the numbers are quite small. Who wants to try this one? 0.01 is the coefficient.
Is that the average increase in glucose levels per increase in negative mood per within persons?
Within persons. So for every unit grumpier than usual,
Yes.
yes, for every unit you are above your mean, your glucose that next morning, specifically, because it's a within person daily parameter here, the next morning's glucose goes up by 0.01 for every unit grumpier you are than usual. So units are very different between these two variables. I don't have descriptives for the observed variables, but I do have the variance components for what mood was if you run it through an empty model. So there's less variance at level 2 than there is at level 1. So the variance for level 2, essentially person mean differences in mood, is 0.38, and it was 0.53 for level 1 differences. So we have to sort of know how big a unit is in terms of standard deviations to think about this in an effect size kind of way, because these are unstandardized coefficients. So simply for the reason that these two numbers are different from each other, that the distribution of variance in mood is not equal across levels, we would not expect their slopes to be equal. You can think of them as literally two different variables on two different scales. So then the whole reason to bother to study somebody for 3 weeks is right here. The idea of grumpier than usual translating into more glucose the next day. Question?
Yes, in this case, Lisa, if we would like to compare those estimates, could we compute some kind of, what is the name of this, partial correlation maybe using the t-test and the estimate?
Yeah.
Because right now they are on different scales, right?
They are on different scales. So yeah, you could turn this t-test statistic into an R or some kind of a D if you wanted to. In my textbook in chapter 8, I tried to do like a pseudo standardization based on the idea of like pseudo R square, where you can like the standard deviation of Y would be with respect to the variance components for glucose, and a standard deviation of X would be with respect to the observed predictors. You could try to do that something like that as well. But yeah, you can't, there's no way to say, well, this number is a lot smaller, so that effect is weaker. They're not on the same scale.
Great, thank you.
Thanks for the question. Other questions so far? So being grumpy is bad for you. Grumpy people have worse glucose. And when you're grumpier than usual, your glucose is also elevated relative to your usual. That's what we have so far. I have an F-test that lumps together those two things. So I'm using contest MD as opposed to 1D, which is multidimensional. And I have two contrasts here. Basically, I'm asking, hey, can you take the within slope and can you take the between slope and can you give me a joint hypothesis test for the two of those? So that's what I'm asking for. And so that gives me a significant result. So this is an analog to the idea of the F-test for the model in regression. Essentially, this would be like the significance test that goes with the total R square for how well this model has predicted glucose. Here are the three linear combinations that I requested. As you can tell from the coefficients, the first two are redundant with what is already provided by the fixed effects. These are not actually linear combinations because there's only a 1 in one spot. And the last one is the only one that I actually needed to ask for. But I have all three labeled so that we can keep track of exactly what these model parameters mean. And because I hate the way R spits it out as separate pieces and I'm not good enough at R to add them all together, I just pasted in the SAS output. So allow me to cheat a little bit here to keep these things a little bit readable. So the two within person and between person is what we have directly from the model. And that is the only possibility. So the reason that I like person mean centering and I recommend it enthusiastically for longitudinal data where it's only about fluctuation is that it's impossible to screw this up. There is no other possible alternative explanation for what the level 2 person mean can be because it only has between person variance. It has to be the between person slope. And likewise, we took out the level 2 variance to create our level 1 predictor. It only has level 1 variance. It can only be the within person slope. And if you leave either of these out of the model, the other one will stay basically the same. And you're assuming that whatever you left out has a slope of 0, just like any omitted predictor in the history of the world. This thing right here is the new piece of information that may or may not be useful to us depending on what we want to know, but I want you to know how to find it. This is the contextual effect. You can explain this two different ways. The easy way is that this is telling you how different the within effect and the between effect are. It's computed as between minus within. So the fact that this is a positive 0.6 and it's significant means that this coefficient of 0.07 is larger at the between level than the corresponding coefficient of 0.01 at the within level. It's a test of the difference between slopes. Another way to say this, I guess there's three ways, but continuing on to the first way, I would say, is that this is your test of smooshing. The difference between the slopes is your test of whether or not it would be okay to put them together and make them one number instead. And the fact that this difference is significant means that would be a bad idea. Question?
Yeah, if both slopes are not on the same scale, how can we compare them directly and compute that difference?
All but we can. Whether it makes sense to do so is a separate question.
Okay.
But if reviewer 2 gets irritated with you because you have negative mood in your model twice and that somehow seems redundant, this is what you tell them. No, those two slopes of negative mood are doing two different things. One is describing differences between people, one is describing within person fluctuation, and here's the significance test that demonstrates it would not be acceptable to make them the same slope.
Thank you, Lisa.
The other way to think about this, which makes way more sense in cluster data and makes way less sense in longitudinal data, is that the contextual effect is the effective person mean negative mood incrementally after controlling for your absolute value of mood at a given occasion. That's the other way to interpret it. And I'm trying to not do that one too much yet. But I want you to know that either of these level 2 effects can be found as a linear combination given the other. You can work your way back and forth, no problem. Okay, how are we doing? Good? Double checking the recording to make sure it looks like it's still working. Hello? Good. I'm paranoid about that. All right, next step, effect size. So
Lisa, I had a quick question
Yes,
before we
please.
move on.
Please. Sorry,
So
Mr.
you
Hand.
mentioned that if you leave one of these effects out, you assume that that one that you left out is 0, right?
Yeah.
Now, so like if we only had the within person effect in our model here, we're assuming the between one is 0. Does our within person effect like estimate and p-values and do those things change, or do those things stay the same?
They should stay pretty much the same if you have balanced and complete data. They may wiggle a little bit if you have different numbers of occasions per person contributing to the estimation, but they should be pretty much the same. Yes. So to me, even if the between person effect were non-significant, I'd probably still be inclined to keep it, because it's weird for me to think about the effect of more than usual but then not have usual in the model somewhere as the point of reference. Like, to me, that's weird. It's not wrong, though, if you wanted to take one of these out. Questions in the chat, let's see here. So if the contextual effect were not significant, would you still want to keep it, the slopes separate? This is where I would disagree with other people. So the argument for, well, the contextual effect's not significant, that means these slopes are not of different sizes, let's just put them together. The argument for that would be to simplify the model, that theoretically you would have more power for a single slope than to split it across 2 slopes that are of equivalent size. The reason that I say no, you still keep them separate, is because this is only step 1 of a 16-page handout. So what do you think might happen if I were to add another set of predictors to the model? Well, each of these effects is going to change if those predictors are correlated with negative mood. And usually the predictors that we're looking at are part of a constellation of commonness where their effects will change once they become unique effects controlling for something else. So you would have to recheck the contextual effect at every step of your analysis to make sure it's still not significant, given that the slopes are going to wiggle around as they become adjusted for the effects of other predictors. Likewise, let's say that we add interactions to the model. What if I want to look at gender differences and the extent to which negative mood translates into worse glucose? I can do that. But then these become simple effects. And so a contextual effect may be non-significant for one level of a moderator. It could become significant for a different level of a moderator. And so I don't like all of that wiggliness. I like, even though it may seem unnecessary to have extra things in the model if they're not different, I like that it clarifies the interpretation. No, this is about differences between people. This is about fluctuation within people as 2 separate ideas with 2 separate predictors. Another follow-up question, is it rare for the contextual effect to be not significant? I would say this varies greatly by the context of the data collection. So in clustered data, when there isn't usually as strong of a level 2 component, you may not have a significant contextual effect, in part because you don't have a lot of power necessarily. If you have very few clusters and if there's not a lot of variability in your predictor at level 2, then it becomes harder to show an incremental effect of that variability. In longitudinal data, though, usually there's a very strong intra-class correlation. And so there's a lot of variance at level 2. It has more of a chance to show a differential effect than at level 1. Okay, did that answer the questions in the chat or coming from you? Good. Other questions? I like questions. Not right now? Okay, let's talk effect size then. So effect size, we can do a couple different ways. One is an overall effect size. So I used a predict function to compute a new variable in the data set called pred_mood_p. P stands for person mean centering, by the way, as opposed to grand mean centering, which is the second half of the example. And I am computing it using the results from my model saved as fixed within person. And I have reform equals NA. Any guesses as to what that means?
No random effects, right?
No random effects in my prediction. Now, why would I want to do that? The goal of building this prediction, by the way, is to compute a total R-square. That's what I'm doing this for. So I'm telling it, do not put the random effects in my predicted outcomes. Only use the fixed effects to create predicted outcomes. Now, why does that make sense?
Is it because you have if this was like in a multivariate SCM land, the random effects are controlling the variation between the within person effects, so you can only have fixed effects there. Is that kind of it?
Not unless I misunderstood you. I would say that the random effect that we have right now is just an intercept. And so that is controlling for person mean differences. So that much is right. But the question is, why don't I want that random intercept into my prediction? Chat window, only fixed effects can explain variance. Random effects do not explain variance. Yes, that's why. So what's the difference, remember, in linear regression between y and y hat? Remember that, the idea? Y hat is your predicted outcome from the model. It doesn't have an e in it, right? That's the difference. Y has the e because that's the residual that is person specific, and y hat is the prediction for anybody who has the same levels of your predictors. Well, if I wouldn't put an e in it, why would I put a u in it? U's are error terms. U's are, I don't know why you still need a different intercept, but you do. So yeah, I would say that it's not cool to put them in the prediction. Other people might disagree with me. But when I describe total R-square, when I use it in papers, I clarify this is the square of the correlation between the fixed effect predicted outcome and the real one, so that at least people know what I'm talking about. So I made that column without the random effects, ran a correlation, and then printed the square of that correlation, and it's 0.02. So that means that on the whole, mood is responsible for accounted for 2% of my variance in glucose. Which sounds pretty small, but hey, this is based on real data. And there's a lot of things that go into biological variables besides things like mood. And I'm not controlling for a million other things that I probably should have, because I'm trying to keep this example from going off the rails. So if you can forgive me the lack of realism here, just to keep the story relatively straightforward. So as a global effect size, basically, how much does mood predict glucose? The answer is 2% of the variance. A more specific effect size we can get through pseudo R-square relative to an empty model. So I have the empty model variance components for mood in the first row of this Excel chart, and then I wrote in the ones that we just added here, and here's the difference in the variance components. So the question then, which accounted for which pile here? My residual variance went down by 0.002, a tiny little number. Which slope did that one? Which of my two slopes explained the residual variance?
Within
The
person,
time variance.
level 1.
Yeah, level 1. Yep, because level 1 residual. Yep, the within person one. And that means that the other random intercept was explained by softball.
Level 2 predictor.
Yeah, the level 2 person mean. So if I want to use these numbers and describe them, I can't just say, 2.5 or 2% of the variance or whatever. It's 2%, 2.5% of the intercept variance And in the original decomposition of this variable, the intercept variance was about 69% of it. So I have 2.5% of the 69% that was in the intercept. Likewise, I have 0.2% of the 31% that was in the level 1 residual. So these are partitions of partitions. So that way you can get a specific breakdown as to how effective your model is at level 1 and at level 2, as well as a general sort of how well do the levels come back together again. Okay, how are we doing so far? Good enough? Question. I saw it this time.
Question. So, I mean, that proportion is not very big, right? 0.2% of the residual variance. But I mean, I'm just trying to understand like the difference, like practical significance versus like our statistical significance, because the fixed effects are like, they're significant, great. But then like what do we say here?
If you want to say who cares, it's only 0.2%, I would not disagree with you.
Okay.
Keep in mind that this is, I think, 200 fake people times like 21 fake days. So the level 1 sample size is quite large. We have a lot of power to detect significance of tiny, tiny little slopes. I would argue that grumpiness as a whole, as a trait, matters a lot more based on these effect sizes than transient grumpiness. And the idea that I'm calling it a trait is actually potentially testable as well. So we're making an assumption about how a person generally is based on the aggregate of asking them how they are today. That makes sense? Like I ask you every day for 3 weeks, how grumpy are you today? And you tell me. And so then I take the aggregate of that and I give you an average grumpiness, and then I use that to compare you against other people. It would be interesting to find out, hey, if you just flat out ask somebody, how grumpy do you tend to be on average, if they would give you the same number? Because I don't think they would. And so then it's like, who's right? Is it that they just happen to have 3 really crappy weeks, but they're normally very happy? Or are they delusional with respect to how grumpy they actually are? So that's more of a measurement question than a statistical question, but I am making an assumption that I've stumbled onto a trait across the aggregation of a person's daily measures. All right, do you have another question, or is your hand still up? Okay, now it's down. Okay.
Yeah, sorry, it's down.
No worries. Question in the chat, can they get grumpy because you are asking them every day if they are grumpy? Quite possibly. Quite possibly. See, this is the problem, is that if you ask a psychometrician how many items you need or how many occasions you need, we're always going to say more, right? More gives you a more reliable estimate, but not if they lose their will to live before they finish the study. More is not better if they stop taking your measures seriously and they just are like, make it go away. So that's a design consideration that should not be overlooked, is that we could be inducing negative mood by accident. It's an intervention, except the wrong kind. Is it still an intervention if you make people worse? It's an unintentional intervention maybe, but yeah. Well, it's all like that word is always used in the context of trying to make an improvement, right? Yeah, not a successful intervention for sure. I don't know why you'd want to create negative mood. The world has enough of that as it is. By the way, when I originally started this handout like 10 years ago, it was negative affect. And I didn't get through one lecture without saying the effect of affect, like wrong. And I just, so it became mood at some point because I can't handle affect, the effect of affect. All right, so we have so far fixed slope of within-person negative mood. Do you think that there are individual differences potentially in the extent to which being grumpier than usual translates into worse health the next morning? Could be. All right, so this is a random slope model we're doing, except it's not a random effect of time. It's a random effect of within-person negative mood. But it is exactly the same concept. The idea that we have a slope that is on average is your fixed slope. we are allowing individual variation around that slope so that each person can have their own slope. And we're adding one variance to the model for that slope, as well as its covariance with the intercept, and seeing if it fits better. So where is the new term then in the equation that indicates I'm allowing a random slope for within person negative mood? It's like, where's Waldo, equation style? Yeah, you won, right there. So U1 last semester was always some function of time, right? Linear time or piecewise time or something. Now it's mood, but the concept is exactly the same. So I'm going to add within person negative mood to, after the bar thing in Stata, I'm saving the -2 log likelihood and asking for a likelihood ratio test as usual. In R, I'm adding it right here to the end of the equation inside the random part, and also going to ask for a likelihood ratio test with that. So here's my results. I do have a new variance estimate for negative mood that is a tiny, tiny number. R doesn't give you standard errors or p-values with this, but it's just as well because we're not using them for this context anyway. I have my RANOVA function here to ask what would happen if I took out the random slope. So the results are right here. I have a likelihood ratio test statistic of 3.22 for the change in -2 log likelihood relative to the previous model. 2 degrees of freedom because I added a slope variance and its covariance with the intercept. Non-significant result. So what does this tell me in words or English?
There's no differential relationship between within person mood and glucose for people.
Yep, there's no differences across people, and the extent to which being grumpier than usual translates into worse glucose the next morning. Yeah, the slope does not vary. Let me ask you a homework drop-down style question. Does this non-significant likelihood ratio test indicate that I made the model better, not better, worse, or not worse relative to the previous model? One vote for not better. Several votes for not better. That is correct, because we added something. So it's better or not better are the only possibilities. AIC and BIC could actually get worse because they adjust for the number of parameters, but -2 log likelihood does not. So yeah, it looks like we don't really need the random slope. I did have a note here with respect to the degrees of freedom. So previously, the degrees of freedom were much larger for the negative mood effect. It is, let's see here. Yeah, like in the SAS output, it's 3,900 and some odd. That's based on the number of level 1 observations. Whereas once you add a random slope, the fixed slope that goes with it has degrees of freedom much closer to the sample size at level 2. So you can end up with a different hypothesis test result for the fixed slope once you add the random in, not just because the standard error has the new random slope variance in the numerator adding to it, but also because your degrees of freedom become smaller. They become level 2 degrees of freedom, basically. So if this random slope were significant, of course I would keep the fixed slope no matter what, because it's the middle of the distribution. But because the random slope is not significant, I feel like I am justified in getting rid of it. Unlike fixed effects, if you have extra random effects you don't need, that can break your model. That will result in non-convergence and instability of estimation. So I tend not to keep random effects that I don't need if it's decidedly not needed. What if reviewer 2 is like, hey, shouldn't that be a mixture chi-square to test your random slope variance? What do I say to reviewer 2 about that? Do they have a point? Do you remember mixture chi-squares? Mixture chi-square is what you do if one of the parameters is on the boundary of the sample space as its null hypothesis.
Isn't it the case that the change or the difference would be so small that it's not really significant, or not significant in the statistical sense, but like it wouldn't be that big of a difference between the two?
Yep, so the reviewer has a point. This should have been a mixture chi-square. And what that translates to in practice when you're adding a single slope variance and its covariance with the intercept is that your critical value goes from 5.99 down to 5.14. That's the difference. And this test statistic of 3.23 is under both of those. So even if I had done the mixture chi-square, I would come to the same conclusion. It would still not be significant. If you are only adding one parameter, then you can just cut the p-value in half and call it a mixture chi-square, but it becomes much more complicated the more parameters that you have, and you have to figure out which ones are on a boundary and which ones aren't. And so it's not necessarily a straightforward process, but in this context, it would just be 5.12 or what 5.14 instead of 5.99. All right, so we don't have a random slope. I'm still going to go ahead and add gender as a moderator though, because that was my question that I started with. So now my within person mood effect has a gender component to it. So I have centered, I have a binary predictor where men are the 0, women are the 1. And I have put in, here's the main effect of gender, gamma O2. I have included an interaction of gender with person mean negative mood as gamma O3. And gamma 1, 2 then is the cross-level interaction of gender with within-person negative mood. So now how would I describe the within-person mood slope? Your choices are fixed, random, or systematically varying.
Systematically varying.
That's it. What I'm saying is that dudes get one slope and chicks get another, but it's not varying after that. And yes, in the original study, gender was binary. It was conducted many, many years ago. So I'm sticking with the original study for the sake of demonstration, but if you wanted to have extra categories, it would work out the same way. So this practice is also somewhat controversial. There are some people who would say that if you don't have a random slope variance that's significant, then you have no business seeing if you have any cross-level interactions that would predict it. However, I think it's a reasonable thing if you're only forecasting 2 different slopes instead of 1. And this was one of the primary questions of the analyses, is looking at gender differences in these things. So I went ahead and did it anyway. So I've got a bunch of LinComs here because what I'm trying to do is to leave myself a trail of breadcrumbs as to exactly what these parameters mean. And I would recommend that you do this. Your future self will appreciate it, because it can be very tricky after the fact to go back in and be like, what's this mood and what's that mood and what's the level 1 and what's the 2, and like if you figure it out, write it down. So some of these are unnecessary. For instance, I have intercepts for men, women, and their difference, where the first one is directly given by the model. The third one for the difference is directly given by the model. The one for women is what's not given by the model, but I have them all in one place. I have the same thing for the 3 potential effects of within-person negative mood, what it would be for men, what it would be for women, and the difference. The same pattern for between-person effects of negative mood, and then the contextual effects, which are a little bit ugly. So here are the 3 new terms that would allow me to do that. So the pattern of the interactions then, like for instance, if we look at this one right here, I'm starting with the effect of person mean negative mood as the thing I'm interested in, and then I apply the moderation interaction term to it. I turn it on to 1 if I want the moderation to be for women. I leave it set to 0 if I want it to be for men. So if I know, for instance, that this linear combination right here is the between negative mood slope for women, then I can figure out what the contextual negative slope would be for women, even if it's not in the model, as the difference. So I have the between slope right here. Those 2 pieces are the between slope. The within slope for women is these 2 pieces right here. So I am subtracting them from the between to get the contextual effect. And so note that because the negative mood within slope has a -1 here, because I want the difference of between minus within, that -1 also applies to the corresponding interaction term. So it would normally be a 1 for women, but it's a -1 because I'm multiplying it by whatever I would have said already for within-person negative mood. So a lot of linear combinations here. Things that the model gives you directly is stuff for men and differences for women. You get to what it is for women indirectly, you can get to the contextual effects indirectly. And then I asked for some margins and a picture, which I also have in Excel. Okay, any Stata code questions for this? No. All right, then here's my R code. So R has my previous model right here, the 3 new effects of gender, and I'm going back to a random intercept only model based on the results of the previous analysis. Here's our coefficients. Now, who is my intercept for? Previously, it was for a person of average grumpiness when they are at their average. That is still true, with one more addition to that sentence needed.
For men?
For a man, yes. Sex MW is the name of the variable where men are the 0 and women are the 1. Yep. Likewise, the main effects of negative mood, are they marginal or conditional?
Conditional.
Conditional. Who are they for?
Right now, the reference group.
The reference group, which is men.
Yep.
Yep. So in men, for every unit grumpier I am today than usual, next morning's glucose goes up by 0.03. It's actually bigger than what it was before and significant. In men, for every unit grumpier I am than some other dude in my person mean negative mood, my average glucose across all 3 weeks goes up by 0.18. It's actually a much bigger effect than before. If I go to the main effect of gender here, is this marginal or conditional?
Conditional.
Yep, for the same reasons. This is the gender difference in people of average grumpiness when they're at their average, specifically. It's not significant. The 2 interaction terms, they have the same pattern relative to the main effects. We'll do one first. What is the interaction term telling me? The within person negative mood slope for men is 0.03. The interaction of that variable with gender is negative 0.03.
The slope is less positive for women.
Yep, less positive by almost the size of the slope. So in women, it's basically 0. And that effect is significant. So being grumpier than usual matters if you're a dude. It does not matter if you're a woman. That's what these results are telling us. It matters way less if you're a woman. That's a way you can talk about less positive, because it's a weakening of the effect. Matters less. Likewise, the between person negative mood slope in women, I would describe as less positive as well. Almost the same pattern. And yes, this is what we found in the original paper. The effects of negative mood were significantly stronger in men than they were in women. Here's my F-test for the 3 effects of sex lumped together. So does sex moderate my model? Yes, it does significantly. Here's all of the LINCOM results and things. So I'm using Contest 1D to get each of these pieces the same way that I did with LINCOMs and Stata. By now you're very good with the 1s and 0s, right? Like, I hate you for this, but yes, I'm very good at this now. Do we want to talk about the 1s and 0s? Or do you feel good with the 1s and 0s? It's up to you.
I have more of an issue with the negative ones.
Ah, yeah. So like the contextual effects, you want to look at those?
Yeah, but like just even in previous courses when we like last semester, I had a hard time with like using the Contest 1D
So negatives show up whenever you're asking for a difference of slopes.
Okay.
That's as a general rule. If you don't see a negative, then what it's doing is adding all the pieces together to create one new slope. The negatives turn that into a subtraction. So as an example, let's do the contextual effect for men. So the -1 coefficient is applying to the within person slope main effect. The +1 coefficient is applying to the between person slope main effect, because the contextual effect is the difference of the two. So this is translating as between minus within. That's what this pattern is doing. If I had flipped the order of the signs, then it would be the same number, but backwards. It would be within minus between, which is not correct for a contextual effect. For women, actually, let's do the difference first. The difference in the contextual effect for women is the difference between the interaction terms. So this is the between interaction term minus the within interaction term. That tells me how the contextual effect differs between men and women. To get to what it is in women, then I need both pieces. I need what is the contextual effect in men, which is given by those two, and then I add to it the interaction terms that turn on to 1 if I am using women as the moderator. But because of this negative right here, this one also has to be a negative. It's -1 times 1 is how we end up with that. And the other one stays +1 because the between slope was +1. So this isn't sort of an extreme linear combination, but I wanted to show you that regardless of whether you set up your model as within between or some other way, you can get to the contextual effect if that is something you need to have. And here's all the results from that. So we have the within person effect for men, for instance, that was given directly by the model. The difference for women was given directly by the model. If I add those two together, I get to what it is for women. Same thing with the betweens, and same thing with the contextuals. All right, question.
In R, Lisa, why are you using contest 1D instead of GLHT?
Because contest 1D works with the Elmer test function to return the Satterthwaite degrees of freedom correctly.
Right, thank you.
Yeah. I don't know if GLHT works with this or not. It doesn't work with all the packages, I've learned the hard way. But it works the same way as GLHT does. Just it doesn't let you write out words as an option, which is unfortunate, but that's okay. Yeah. So we have then pseudo R-square and total R-square. So for total variance, we're up to 5.6% for my total R-square. Most of that came from adding gender as moderators. Here is the comparison for pseudo R-square. So the previous model that had only the main effects, and then our new moderation model that has 3 different terms related to gender. So then I'm going to ask you the same question. Which pile of variance did each new fixed effect explain? We'll start with the main effect of gender. Did it explain level 2 random intercept variance or level 1 residual variance? Level 2. How about the person mean mood by gender level 2 interaction? Both variables are at level 2, has to be the random intercept. How about gender by within person negative mood? Cross-level interaction. Well, it has to be residual because there's no random slope. If there were a random slope for within person negative mood, the gender by within person interaction would have come out of that slope. But because there's not one, it came out of residual instead. So same concepts as last year, but a little bit more complexity. Here's a picture. I made this in Excel because I wasn't about to fight with R to make this picture. Instead, it made one for me too. So this is the kind of picture that I would make to describe these sorts of findings, where the x-axis is the within person effect. And so note the middle of these things, like it's labeled as usual as the center, right? And then lower than usual and then higher than usual. The values that I plugged in for that were plus or minus 1 because that was roughly 1 standard deviation of the original variable. So you can pick whatever low and high would be custom to your prediction. And then I have different lines for different kinds of people with respect to their gender and their person mean. And again, plus or minus 1 to reflect 1 standard deviation above the mean. So the slopes of these lines are showing the within person negative mood effects. And if you look at the red lines, those slopes are nearly 0. The slopes of the blue lines are positive. That's showing that the within person negative mood slope was more positive in men than in women. The differences between the lines vertically are showing the between person effects of negative mood. So within a color, the solid lines are the grumpy people, the dotted lines are the happy people, and the grumpy people, if you're a man especially, have a higher glucose on average. Same is true for women, but to a much smaller extent. So the gender by between person level 2 interaction is shown by the blue lines being further apart from each other than the red lines are. So this plot, I think, is about as clear as I can make this, because it's like the within person effect is on one way and the between is the other, but there's no way to stick the contextual effect in this plot. So I had to make another plot for the second half of the handout that I will show you that has that in it instead. But that will have to wait until next week. Actually, no, it'll have to wait 2 weeks. That makes you smile. Yes, I know. Spring break, Iowa. Everyone get their skis out. All right. Oh yeah, I forgot. I did this in M+. Like, oh yeah, here's another model. I completely spaced that I made this. So this is the last model in M+. The key thing here is that I'm using variables for my within person negative mood. So on the within line, I have my within person. On the between line, I have gender and my between person negative mood and their interaction, which I made here. So this is what it would look like to fit this model in M+. I did this just because so many of you are going to be making the transition into multi-level SEM, but otherwise there's no reason to do it this way. You're not gaining anything. You're actually losing Remel estimation and denominator degrees of freedom because this is maximum likelihood with z's and chi-squares. One thing that I don't know that I've shown you yet is the idea of model constraint. Have we done that in this class? I don't think we have. Does that sound familiar yet? Okay, that will have to wait till next time. But this is basically the analog of LINCOM or Contest 1D. The key is that you have to label your terms first, and then you can use those labels down here to make it do math. So, all right. I'll pick that up next time, and the rest of the handout will have to wait until after break. Any questions before we call it a day, a week, not quite a month?
Lisa, I have a quick question
Yeah.
specific to my project after, if that's okay.
Okay, yep, I will stay on the line and talk to you, and I'll let everyone else go unless they have questions. No questions. Okay, well, have good breaks, people. Make sure you take at least some time off. Have a little bit of fun, get some sleep, and I will see you in a week and a half. Thanks for being here. Happy snow day.